Beijing researchers have unveiled a startling solution to one of the most persistent headaches in stealth aviation: worn-out radar-absorbent coatings on fifth-generation fighters like the F-22 and F-35. Instead of inventing a completely new material, they turned to a technique that dates back more than 3 millennia. During the Han Dynasty, around 200 BC, Chinese artisans wove intricate brocade patterns using multi-arm looms, precursors to later Jacquard concepts that encoded designs into the fabric itself. Modern scientists have reinterpreted that ancient brocade method for the 21st century battle space. By integrating conductive stainless steel yarns and quartz fibers into a warp-knitted, double-layer structure, they have produced a composite fabric that reportedly absorbs over 90% of radar waves across the 8 to 26 GHz range. In practical terms, a fighter cloaked in this woven composite would reflect almost no return to enemy radar for hundreds or even thousands of flight hours. The problem with present-day stealth coatings, those painted multi-layer radar-absorbent polymers, on aircraft such as the F-22 Raptor, is well known. These layered paint systems begin to degrade under high-speed flight stresses, extreme temperature swings, and even routine ground handling. In desert environments, sand and grit can scour surfaces so aggressively that coating cracks appear within weeks. Maintenance crews currently must repair or reapply radar-absorbing material every 20 to 30 flight hours, at a cost running into tens of thousands of dollars per flight hour. Those recurring expenses, plus the downtime required for reapplication, erode both readiness and budgets. In contrast, the new brocade-inspired fabric embeds radar-defeating structure into every fiber, making it far more resilient. Tensile strength tests performed in research labs indicate that the composite can tolerate stresses exceeding 1,000 MPa, that is more than 10 times the pull strength of typical polymer-based coatings, without tearing or significant degradation. Even after simulated abrasion of several thousand cycles in a sandblast chamber, the fabric retained roughly 88% of its radar absorption capability. Constructing this material requires 3 core elements. First, a warp-knitted quartz fiber base acts as a dielectric substrate, reflecting and slowing incoming radar waves. Interwoven on both faces of that substrate are stainless steel yarns, each about 0.15 millimeters in diameter. Those metal threads form microscopic resonance circuits, tiny loops that convert electromagnetic energy into heat and dissipate it harmlessly. The finished composite is about 1.2 millimeters thick and weighs approximately 1.3 kilograms per square meter, making it both lightweight and robust. By comparison, conventional radar-absorbent paint layers often exceed 3 millimeters in thickness and weigh nearly 3 kilograms per square meter. In other words, this woven fabric enhances stealth performance while reducing both weight and maintenance demands. Historically, the Han-era brocade looms did not use punch cards. Instead, they relied on a system of multiple heddle rods to lift specific sets of warp threads and create geometric patterns. These multi-arm looms, refined over centuries, laid the conceptual groundwork for pattern-encoded weaving. In a modern adaptation, high-precision Jacquard-style looms feed in stainless steel and quartz threads instead of silk, automatically generating complex layouts designed to trap radar across multiple frequency bands. The result is a fabric where each fiber's position and orientation is calculated to interact with specific radar wavelengths. Because the radar-absorbing function is woven directly into the material, there is no separate paint layer to peel or chip away. The electromagnetic properties are intrinsic to the fabric. In practical testing, a 1.5 m times 1.5 m panel of the dual-layer composite was bonded to aluminum skin akin to that used on a fighter's lower fuselage. When exposed to an X-band radar at normal incidence, the panel reflected only about 8% of the signal, compared to roughly 45% for conventional multi-layer RAM at the same thickness. Even at an oblique 30 degrees angle, radar returns remained under 12%. Technicians then subjected the panel to 250 hours of temperature cycling between -50 degrees Celsius and 70 degrees Celsius, followed by 500 abrasion cycles using quartz sand. No delamination or cracking occurred, and radar absorption dipped by merely 4% over that period. By contrast, traditional stealth paints typically require patching or recoating after roughly half that exposure. These metrics suggest that an F-22 cloaked in the new fabric could remain mission-ready for over 1,000 flight hours before needing any maintenance, an order of magnitude improvement over current standards. Beyond fighters, the woven composite promises to improve stealth for other platforms as well. Chinese naval engineers are already exploring its application on ship superstructures. In scale model tests of a Type 054A frigate's mast panels, researchers observed an approximate 35% reduction in X-band radar cross-section when composite panels were applied in targeted areas. On armored ground vehicles, prototype H-shaped panels showed about a 40% decrease in Ku-band radar signature compared to steel plates coated with standard absorbers. Because the material is flexible, mechanically robust, and resistant to saltwater corrosion, it could offer a low-maintenance upgrade path for ships and vehicles operating in harsh environments. In parallel, Chinese academics have begun investigating how the same weaving principles could shield jamming antennas or active electronically scanned array radar apertures. By patterning conductive fibers with specific phase delays, it is theoretically possible to create a metasurface that both absorbs incoming radar and shapes outgoing signals. This could lead to future aircraft skins that dynamically adjust their radar profile, minimizing detection by hostile systems while still allowing the aircraft's own sensors to function unimpeded. Deploying woven composites on a full-size fighter presents logistical challenges. Existing production lines for stealth aircraft parts are configured for pouring and curing polymer coatings or bonding rigid composite panels. To transition to a textile-based system, China's defense industry has invested in specialized Jacquard-style looms capable of handling high-strength stainless steel yarns while maintaining micron-level precision. The first of these machines became operational in mid-2024 at a facility near Suzhou. There, technicians fine-tune tension controls to prevent wire breakage and adjust weaving patterns for optimal electromagnetic performance. Early output is slated to supply test airframes of the J-20 and J-31 fighters later in 2025. If all goes according to plan, initial squadron-level introduction could follow as early as 2027. From a strategic standpoint, this development could shift the stealth maintenance balance. In the U.S., Lockheed Martin's F-22 fleet has been hampered by frequent radar-absorbent material repairs. According to publicly released budget summaries, up to 30% of F-22 downtime is attributable to RAM maintenance, contributing to mission-capable rates that fall below initial design targets. If China outfits its entire J-20 fleet with this woven composite, its fighters may remain stealth-effective over longer deployments, giving it a durability and readiness edge. That, in turn, complicates adversaries' counter-stealth efforts, since radar systems tuned to detect small signature leaks would face fewer opportunities to peek through coating gaps. Even with these advantages, some technical hurdles remain. Welding stainless steel yarns into a warp-knitted structure raises concerns about embrittlement when exposed to extreme cold, below -40 degrees Celsius, during high-altitude operations. To mitigate that, researchers have introduced a thin polymer interlayer at yarn intersections, allowing controlled flex without cracking. Similarly, while quartz fibers excel at high temperatures, they are more brittle than carbon fiber composites. Teams at Tsinghua University have experimented with hybrid braids that combine quartz and high-tenacity Kevlar to improve impact resilience. They are also exploring surface treatments designed to reduce radar scattering at higher V-band frequencies, which will become increasingly important as adversary radars migrate to higher bands for imaging and target discrimination. The cost to retrofit an entire air fleet with woven composite panels is not insignificant. Early estimates suggest that once production is stabilized, material costs could range between $2.500 and $3.500 per square meter, compared to roughly $1.200 per square meter for high-end polymer-based RAM. However, when factoring in life cycle savings from reduced maintenance, higher operational availability, and less downtime, the break-even point may arrive in as few as 200 flight hours. For a single J-20 squadron flying 2,000 hours annually, that translates into approximately $10 million saved each year in maintenance alone. Looking ahead, China's woven stealth fabric could inspire new defense doctrines. Rather than rotating squadrons back to base every few weeks for coating reapplications, operational planners might deploy high-readiness stealth packages to forward bases, secure in the knowledge that aircraft can remain cloaked for months at a time. This persistent stealth capability erodes adversaries' reliance on predictable maintenance windows to mount radar surveillance or targeting missions. By shrinking those windows of vulnerability, Chinese forces could operate with greater freedom in contested airspace.